Everyone, we're back with the final intro video on LaserTRAM-DB, time-resolved analysis, processing of your laser ablation data. And this episode, or little tutorial, is going to kind of walk through how to take the output from either LaserTRAM Spot or LaserTRAM Profiler and use something called LaserCalc to turn those normalized ratios into concentrations. We're going to go through each of the little parts here as they populate. First things first, we're going to upload our data, and there's two things that we need to upload. One of them is our output from LaserTRAM Spot or Profiler, and the other is a library of preferred standard reference material compositions. And that comes in the test folder. It's the LA-ICP-MS standards tidy folder, and that looks like this. It's just a table that has a bunch of standard reference materials and their GeoRem preferred values. So if there's a standard that's not in here that you want, you can just append it to the bottom here and fill in all the requisite information on down the line. So with that, we're going to upload it to the dashboard. We're going to close it first, and then we're going to upload it to the dashboard. All right, that's in there, and then we're going to upload our output from LaserTRAM, and so that's in the tests folder. That's this LaserTRAM complete file. This table on the left populates, so that's all of our spots that were completed, and an initial guess for the internal standard concentration here. Our internal standard for this was 43 calcium, and so the table is saying input your internal calcium oxide weight percent values, because you've likely generated these on something like the microprobe, and their percent standard error or uncertainty. So with NIST 612, I don't know that off the top of my head, so we can go back into this spreadsheet here. These incorrectly named NIST spots are masquerading as unknowns, but they're actually NIST 612 analyses. So we'll go find what their calcium value should actually be, and we can see here that it's 11.9 weight percent. So we'll put that in as 11.9. And I'm just manually entering these here because there's so few of them, but these dash data tables also accept and paste from Excel. So if you find that you want to organize, all of your unknowns in the same order that your probe data in the same order that you measured your laser data in, or make a quick table of all your internal standard values, you can just copy and paste from Excel and fill out a table relatively quickly and save yourself a lot of time. And then the next thing for us to do is to choose a primary standard. I'm going to go ahead and choose BCR2G here. And this is a good time to remind you that if you haven't named your spots properly, it's not going to show up as a potential calibration or primary standard. So it's really looking for that GeoRem name here, this name that's in the leftmost column. And if it doesn't see that anywhere in your spot name, it's going to not flag it as a potential primary standard. And that's why these NIST 612s are treated as unknowns. We don't have to input anything for the standard reference materials because LaserCalc is actually going to go into that database and find all the information for the internal standard concentration. And so all that's left for us to do is hit calculate. And what we'll see is that this table populates on the right here, and it's going to be in the exact same order as the table on the left. It's just going to be missing our primary standard. So you'll notice that BCR2G is not anywhere in this list. Another thing to note is that it's relatively easy to now move between different primary standards, and it'll just recalculate everything on the fly. So that's nice for you to be able to explore the impact that different primary or calibration standards have on your data, and you'll find that there is a difference, and it's up to you as a user to kind of know which one's best. I personally think that the GS glasses are quite good, and things like BCR are nice, but that's beyond the scope of this video. Anyways, now what we can also do is we can also change these values if you realize your unknowns are incorrect. Move to something egregious like 50. We'll see that that value also changes to reflect that instantaneously. So all these tables are linked, and really easy to manipulate and get your data quite quickly. If we want to inspect the primary standards to see how good they're doing and if they're drifting over time or something like that, we can go up to this primary standard data tab. If not, we can just hit export and be done with it and get your data, and that has our timestamp and spot columns that are linking through everything, and now it has our concentrations, and now columns for external error and columns for internal error. So the difference between these two is that external error is including the uncertainty in our primary calibration standards, and by and large this is the uncertainty value you should use when you're comparing between data sets. If you're only comparing internal uncertainty, so data uncertainties within your own data set, you can go ahead and use this internal uncertainty. So that's not including uncertainty in the primary standard. That's the only difference between those two. The internal error is always going to be smaller than the external error, so it might be tempting to use that, but when you're comparing between other labs and other data sets, that's not the correct choice to use. So to look at our primary standard data, we're going to hit this primary standard data tab over here, and this is going to give us a plot on the top of our normalized ratios for our primary standard over time, duration in the experiment here. So we can inspect any element in our experiment. We'll see this one will be exactly 1 for 43 calcium. That's good. And we can go through and see whether or not things have been drift corrected. And from the documentation of LaserTRAM, you can go read about how drift correction is happening. Basically, in brief, it needs to be a statistically significant regression. So there's something called an F value. The F value needs to be bigger than the F critical value, and the P value also needs to be significant. And this table here is giving us basically everything that we need, all of these statistics for our primary standard. So you can really get into the weeds of how your primary standard is doing. So there's a column for the analyte, whether or not it's been drift corrected, the significance of the F p-value, so things that are below our drift significance threshold here don't get drift corrected. If they're above it, they get drift corrected. So we default to 1%, which is a pretty harsh line, but it means that nothing but the most linear drift gets corrected, which as a default is a good rule to follow. And then there's columns for the root mean squared error of the regression, and then the slope and intercept and mean, standard deviation, all of these things, such that you can make plots and do statistics on your primary standard data if you really want to. And just like any of the other tables in here, you can export it and it'll save an exact mirror of this table. And with that, we have our concentrations and a metric to see, both their internal precision and external precision, and also how well our primary standards are doing over time.